Well, since I got this video fired up, because it's described what it is, just so I don't have to go through the hassle of trying to get it up again. So what is this? This is passive radar. It's something that I've been interested in the last month because of my work at HSTAC. My colleague, Frank Lin, did his PhD on passive radar, and he's got a project where he wants to expand passive radar into passive radar imaging, where we use we use transmitters of opportunity to illuminate targets such as unclear irregularities or meteors, spectral meteor echoes. And for that we need multi-channel receivers which are coherent, and the bare minimum that you need for doing a standard passive radar experiment is 2 coherent channels. And USRPs are really good for doing this. I bet you could do it with the USRP-1 too. And definitely done it with the USRP 210 and then 200, but this video is special because I did it with the 8-bit RTL SDR dongle. So I was surprised that you can passive radar with such limited dynamic range. I wrote something about this on my blog, and something you can find the link probably by googling passive radar and maybe RTL SDR. And in this video, all these small dots are echoes from airplanes flying above New England, probably going to Logan or Hanscom Air Base or somewhere there. Now on this axis, on the lower axis, on the x-axis we have Doppler shift. This is basically the change of the path length from transmitter to receiver. And here we have range, which is basically signal propagation distance, which is more than the distance from the transmitter to my receiver side. And the furthest thing that you can, sometimes you can even see airplanes which are about almost 2,000 kilometers away. And you can see here, spectral meteor trail echoes because they're usually have stronger radar cross section than airplanes. Okay, so yeah, those in this part. So this is this is what an HF heater looks like inside. So conspirators and theorists would walk inside one of these buildings which is unlocked and it's full of 60s equipment. They wouldn't be so scared of them. It's just basically a very high power 2 megawatt transmitter with a high gain antenna that can be used to carve track battery structures to the atmosphere. This is what they look like. This is the HF. You can't really see it. Okay? Well, this is the UHF antenna, this is the VHF antenna. This is about 140 meters in this distance and then 40 meters here. And this area here is a huge array of cross dipoles, which is the HF heater transmitter antenna. And it's got about 25 dB of gain at 8 megahertz. And what the experiment that we wanted to do is that we provide a lot of dynamic range and synchronization is called the artificial periodic regularity experiment. I didn't come up with this, some Russian dudes did. But what you do is you transmit 1 megawatt or 2 megawatts. It reflects from the F layer, the ionosphere, total reflection. And then the wave comes down, and part of the wave, because it's in the same frequency, it interferes and constructively and destructively at wavelength divided by 2 intervals. And you do that, and you have high power. What you're doing is you're causing the temperature of the ionospheric plasma to change ever so slightly at the Bragg scale. And once you've done this preconditioning using the heater, you can get them send radar pulses and there'll be very strong reflections from the ionosphere. And this is a very useful method for remote sensing of the B region, which has very low ionization, and can't really measure that region of the ionosphere very well with for example, these large incoherent scatter radar. But using this method, we can do it. And here's an example of an echo that artificial periodic irregularity echo. These are typical echoes that ham radio people operating on HF will rely on for perfectly detecting their signals between the Earth ionosphere waveguide. But this stuff here is something that we've done ourselves. We've carved this scattering structure in the ionosphere using the heater, and we use the USRP M200 to act as a very high dynamic range receiver to get echoes with these kind of power levels actually on our signal cable without any amplification. So you imagine a radar echo with a 2 volt peak to peak without any amplifiers. Yeah, the way we did this, the way we got more dynamic range is we basically sampled 2 channels at 10 megahertz, and our analysis bandwidth was about 33 kilohertz. So we transferred that 2-byte integer signal into the processor as soon as possible at 10 megahertz, and then it did all the rest of the filtering and decimation in single position floating point, which gave us a lot more dynamic range than we would have got with 16-bit integers. A colleague of mine, or a friend of mine, Dave Heisel, he's going to go to Harvard pretty soon, and he's going to have one of these N200s with him, and he's going to use Harvard, the Alaskan US equivalent of the high-speed heater to do a similar experiment. Well, I don't know what I'm going to say here. Just wanted to show off that I've done this. It's fun to have a lot of USRP receivers. Our purpose was to demonstrate a phase array radar receiver, and with these devices, it was easy to do it. We could tell our financiers, our sponsors, that it's going to take at least 2 years to do it. It's going to be a very hard job, and then 2 weeks before the deadline, we should do it. Here's one of these rack mounts going into a phase array test receiver here in Sweden. This happened just 2 weeks ago. Okay, my favorite radar, the Nico marker radar in Peru. It's the largest incoherent scatter radar in the world. You can't really see it from here, but you can Google it. You can find pictures. 300 meters times 300 meters, and it has countless dipoles. And it operates at 49.92 megahertz. During my PhD studies, I was a summer student there. I implemented a general purpose radar experiment that could look at all different regions of the ionosphere at the same time. And again, this was very easy to do by just plugging in my USRP1 and gathering echoes and throwing different signal processing and radar signal processing tools for it. These are echoes from the equatorial vector jet, and this again shows you that you can get pretty high dynamic range and you still don't get phase leakage after the pulse compression, because even the USRP seems to be linear enough in this region. Some other echoes that you see using the echo marker radar. These are all ionospheric irregularities that are typical of the close to the magnetic equator. These are so-called 150 kilometer echoes. Nobody even knows the mechanism of why you get these echoes, so it's interesting to get good measurements of them. Here again, some strange echoes that I've just recently discovered. My general purpose experiment picked them up. They're these kind of finger-like echoes, probably again caused by ionospheric irregularities, but they're the float going up upwards of 2,500 kilometers in altitude. And typically the ionospheric echoes that we see the Korean scatter, it stops at about 800 to 900 kilometers. They're really almost vacuum here, so it's got to be a irregularity. Mesospheric echoes, these are mesospheric turbulence in between 70 and 80 kilometers. You can do all kinds of power using these echoes to determine 3 vector velocities of wind, for example. Here's a general overview picture of my all-purpose experiment. This is what the market experiment looks like, but you zoom into these different regions, you see different things. And it's always nice to have IQ samples that you can reprocess using different settings. Got something from Haystack too. This is 6 months ago I started here. I'm pretty happy to have big radar outside, so I can play with it every now and then. We installed receivers at Haystack too, so we've got this rack mounted. It's actually an idea of rack-mounted colleague of mine. This idea was let's buy this shock mounted rack that you could log to check into an airplane, and then install USRP and a server and the output clock and network switch and everything into this thing that was the size of a suitcase. And we've got still these now, and we're really looking forward to doing all kinds of measurements all around the world. But with Haystack, one of the first things that I did was I used the 25 megahertz bandwidth that you can do with you can get with USRP2, and basically went after the plasma lines. Plasma lines are basically they're Blackbird waves, they're oscillations of electrons in the plasma. And normally these are not measured at Haystack because the RFI situation there is very horrible. You have 50 dB stronger interferers in your band, and you really have to line up your receivers pretty near in order to filter them out. And it turns out you can really do it, and you can get plasma lines pretty accurately. And this was the first time that we got a plasma line profile out of Haystack. And this is very useful because we can improve our electron density estimates by 2 orders of magnitude, from 10% to maybe even 0.1%. Depends on the situation, how long you integrate. But and then this is what this narrow line in the middle is what's normally measured at a radar. It's a major improvement in our capability of a radar, which was built in the 60s. Okay, I don't know how much time I have left in the last speaker, so I can simply talk as long as I want. Showed you some large radar measurements. I like large radars, but in recent years I've started to be more and more interested about small radio science remote sensing instruments that can use to sense different geophysical aspects of the ionosphere. I'm going to describe 3 different small instruments that anyone can do at home. You can just have an antenna or a USRP, and maybe you can use some of the software that I have published. Who knows what an ionoson is? Raise your hand. An ionoson. Well, Matt knows what it is. Donald knows. Jonathan Corbin knows. Okay, so so an ionoson is an HF sounder, an HF radar. It transmits small pulses at different frequencies between, say, 0.5 megahertz and 16 megahertz. And depending on what comes back, you can determine what the electron density is. And this is a typical ionoson measurement. It's called an ionograph. What you get is you get total reflection at this frequency from this altitude. And this is all determined by the Appleton-Hartree equation. And you measure it at all of these different frequencies, and use the Appleton-Hartree equation. You can convert the electron density profile of the ionosphere using a very low power HF radar. And it's a very old type of ionosphere remote sensing instrument. Geophysical observatories all around the world have these. Air Force operates a fleet of these. These are useful, for example, for predicting radio propagation conditions on Asia. And so what I did is I wrote software to listen to a specific type of ionoson called a church sounder. And they're ionosons which are vertical incidence sounders, and they're also over-the-horizon radars all around the world operated by militaries, sending out megawatts of power. And they're basically sending out an FMCW shirt. And using the USRP2, you can sample 25 megahertz. You can sample the whole HF band, and you can basically listen to all the church sounders around the world at the same time. If you have enough computational resources. Turns out I have enough on my PC. There's enough to look at 6 at the same time, but it's already pretty good. Released this, it's called the GNU church sounder. Pretty sure the code is not compatible with 3.7. Probably not even compatible with 3.6, but a couple of people have sent me email and told me that they successfully used this. And they're probably, anyone working on the HF is probably familiar with these signals. The spectrum, if you see this kind of red, very narrow frequency that goes up in frequency, that's a church sounder somewhere around the world. And looks like this. If you analyze it carefully, in the standard way that you analyze FMCW, you can look at the fine details of this frequency ramping, and you can actually extract information about propagation. So this line here would be could be maybe 2 hops between the Earth and the atmosphere on its way from Cyprus selected where I was doing the measurement, and this would be 3 hops of that region it goes. And there's a lot of wealth of information that you can get also from off-league minus-on soundings. And the USRP2 is a very good instrument for making very good minus-on receiver. We're using this on the observatory for minus-on soundings. We replaced basically a big cabinet of analog electronics with just one USRP and a PC. But this is what I really want to do. I don't think FMCW is in any way a good radar content waveform. I think it sucks. You need a lot of power. You need a big antenna. What I really want to do is I want to do a low power, low cost, small footprint minus-on. Minus-ons, even though they're cheap, they still cost 50K to 100K, and they require huge, 20, 30 meter masts. You don't need that. If you have 80 dB of signal to noise ratio, you can throw a little bit of it away, and you can regain some of that back by using intelligent coding methods. And this is a concept that I showed to people that I tried to pitch this idea. I've actually implemented it just from the office supplies budget. You don't need a lot of money to implement something like this. Features of this minus-on is that it's got very low transmit power. You can operate with milliwatts of transmit power. It's frequency hopping, it's broadband. My transmit waveform is basically a very long pseudo-random noise waveform. It's not going to interfere with anyone. Ham radio people are complaining, and workforce is complaining that minus-ons are causing interference. And that's true. They transmit with very high power, and they transmit pulses. And they basically jam the whole HF back sometimes. But this one, you can't even detect. So it's got a very low probability of intercept. You probably wouldn't find it because it's so much below the noise level. And of course, I want to meet this kind of a price tag, and I think it's possible that if I can meet this kind of price tag, I can think of large networks of minus-ons which are making a volumetric electric density measurement of the atmosphere. Really hasn't been done yet. Okay, that was the hype. This is reality. This is my receiver. It's a 2 orthogonal hula loop magnitude antenna receiver. You do O&X mode to a circular mode of polarization. This is an example of a single frequency. I did this at Eagle Markup this summer. You can't really see it from here, but you've got echoes from the electrojet, the X region, some atmospheric irregularities here. It should be an airplane here. I didn't know that you could see an airplane echo with 20 watts, but if you build a 2-dipole antenna radar with 20 watts, you can see airplanes. You see some meteor echoes here too, waves in the atmosphere. Here I'm using Doppler shift coloring, so everything that's stationary is green. Blue is blue shifted and red is red shifted. And it's a nice way of combining a lot of Doppler spectra into one range time intensity Doppler picture. I'm going to try to zoom into here because I think that speckle there is an airplane. Okay, it's not going to happen. If you're interested in seeing an airplane echo, just come watch the presentation. This is how sensitive you have a 20-watt megaton would be to get almost 20 hops between the Earth and the ionosphere. You know, the radio wave is bouncing between Earth and the ionosphere. Earth and the ionosphere. It takes about 20 hops for it to die down. It's small enough that I don't see it anymore. This is an interferometric measurement. It's got color. Production is not very good, but doing interferometry with this too, you can get angular while here in this plot, green is basically coming from straight up, and blue and red is coming from left to right. Just a simple tool antenna interferometer, but again, it gives you a lot of information about where in the ionosphere the echo is coming from. Supposed to be an airplane echo, you can barely see something there. And then, I thought, okay, there was single frequency.